Morning, everybody there. Hello. All right, thank you. Okay. All right, give me a second here, please. I need to get my eyeglasses so I can see all your smiling faces. Okay. Sorry, folks. I know I am running a little late this morning. I apologize for that. All right, let's get started. We're talking about actually. Can someone tell me if they can hear me? I don't hear any audio. I'm going to make sure.
Yeah, we can hear you.
Oh, excellent.
Yeah,
That's
I
great.
can hear
Yes.
you.
That's good. Now I can hear you. That's good. Okay, so what we had done so far was gotten through question 1 pretty much on the test. We're now going to move on, and let's see, we'll use the printable notes here.
I have a quick question.
Yes.
Because I missed the first class, but I did go watch the videos, and I haven't taken a chemistry class in a long time, so feel free to, I mean, I could just be like completely clueless. And I felt like I was understanding the equations you were doing, but why does it say, like, even for question 1 at the top, I guess the two questions are, it says A plus B equals C, but and then you have this other equation. Like, is that just a standard equation for that, like, that specific thing that we'll see?
I don't know. I'm not sure exactly which one you're talking about. Are you talking about, hang on, let me see.
On the test quiz.
On the test quiz. You mean for question 1?
Yes.
A plus B equals C.
That's what it said at the top.
Oh, yeah. No, okay, no. That's just that's just a reaction. It's just generic. Could A and B could be anything, and it doesn't matter what they are. It could be any compounds, any elements. It doesn't really matter.
Okay, and then I understand the equation that you actually did and how you did it and how you got the answer, but I mean, if you're just looking at the equation, I mean, if you're just looking at the question, how did you come up with that was the equation besides?
Oh, you don't.
Like,
you don't because it was already given to you. No, that would be given to you. You don't have to. You would never have to come up with anything like that.
Okay.
All right. That's all part of what you were presented with.
Okay, because when I looked at the test quiz, I was like, okay, I see how he got that, but if I didn't have that equation, which in the test quiz, it doesn't show that exact.
Yeah, you would. You'd have it. You'd have whatever was required. You wouldn't need it. You actually don't really need it, to be honest. But it is consistent with what's in the table as well, which says concentration of A, concentration of B, and that's the A and B from the actual problem, from that equation. Is that okay, Caitlin?
Yeah, I'll ask you questions as you continue on.
All right.
And then I wanted to let you know too, the videos that it says that has links in the My Course to watch before the courses.
Yeah.
For me, at least, the link wasn't working. I saw that you have a YouTube page, so I just went to that YouTube page and searched it. But when I actually tried to click on those links to watch the video before today's class, it said error not authorized.
Well, you're talking about from the syllabus, or?
Correct.
Okay, well, maybe I need to fix that, because that might be something that flips over from course to course, and I might actually have to change those links.
Okay, I tried a couple of them and they didn't work.
Okay, well, for everybody in the class, go to the mini lectures folder and go from there. That would be my advice. I might even just make them not links anymore, and just just make them just regular text to force people to go back to the mini lectures. So I'd say that if anybody who's on the call here, just go to the mini lectures folder and go directly from there. That would be my advice. It looks as though I thought the links would transfer from course to course, but when I copied it over, it looks like they don't. So I'll have to I think I'll have to get rid of those links, but that's the reasoning there. All right. Any other questions?
Yes, Dr. Musgrave.
Yes, Lonnie.
If for those who want to follow up, in the text, are there certain chapters that we can look at, or
no, not really.
What's the best way to do that?
No, it just follows pretty much the same order. I mean, it starts at kinetics, which is like chapter 13 or 14 or something like that, and then you can go from there. But really, it's really just a secondary reference. I would be more inclined to use the index if there's something specific that you want to know. Then you can go to the book and use that as a source of greater information, if you will. But everything you need is in the course. Everything you absolutely need is in the course. The book is just a secondary reference. That's why I haven't really included anything to it, because it's not really needed. But I want people to have it there just in case they need it. And that's why I suggested getting an earlier edition that only costs like $20, so that they could have that there with them and it wasn't going to cost them a whole bunch. But if you need anything specific, you just let me know, right? If you say, look, I need much more information about this, you can always ask my assistants, and I can try and help you find other resources. And certainly if I can't help you with whatever you're looking for, yeah. Not that I can't imagine that would happen, but it's possible, I guess. All right, we'll move on to single order reactions. Does anybody get any other questions?
I have a question.
Yes, Oliver.
I tried to watch the video before the Zoom session, like last night, and it wouldn't let me do it.
If you were doing it were you doing it from the syllabus?
Yes, sir.
Yeah, I have to change the links in the syllabus. I copied them over. I thought they'd still work from last semester, but they don't apparently work because they're in a different course now. So you'll have to go to the mini lectures folder and watch the video from there.
Okay, the mini lecture folder.
Yeah, it's in test 1. I'll show you.
Okay.
Hang on. Let me get over here. Yeah, I'll show this for everybody so you can see it. So we're in the test 1 folder. And these are the mini lectures here. These are the same videos that I got in the syllabus. Now, those links would definitely work. There's no question about that. But I have to do something with the links in the syllabus. And I'll probably just end up making them not links anymore, so that you'll have to go back to the mini lectures folder to view them anyway. All right, do you all see that?
Yes, sir.
Okay. Does anybody have any other questions before we get started? All right. Okay, so let's go back to what I was doing. Was here, right? Okay. Close that down. There we go. Okay. So last Tuesday, we were looking at reactions that were of this type, where we had 2 reactants and we were varying the amounts of concentrations of the 2 reactants in order to determine what the reaction orders were from the rate equation, which we were not given initially. But if you were not given the rate equation, then we would use the kind of math that I went through on Tuesday in order to this kind of stuff here, in order to determine this M and N value for the rate reaction order. Now, the ones we're going to deal with today are kind of like a special case. It's a situation where we've just got one reactant and it's going to products. And the kinds of situations we're dealing with here will just be when we have the rate being zero order, first order, and second order. So the rate equation for all of these is going to be rate equals K, A to the N. So Caitlin, you were asking earlier about certain reactions and what the A plus B gives C means, but in this case, the A could be anything. It could be any compound, any reactant we like, just that there's a single reactant. And the N value we're assuming can be 0, 1, or 2, and rarely 3 or more. Now, what we're going to see this today, is that there's going to be a link between how the reactions proceed and what the rate equation is. So if you've got a situation where let's say the rate equals, this gives you an idea as to why we don't go this route, but let's say rate does equal Ka to the 3. What that would indicate is that in the slowest step of the reaction, or it might even be a single step reaction, we could say, the 3 there would indicate that there are 3 molecules of A all joining together at the same time. And that would be rare. I mean, it could have happened, I suppose it could, yes, but it would be unlikely. You know, 2 A's coming together would be fine, but 3 A's coming together exactly at the same time would be pretty rare. So that's why we say that the N value would be rarely 3 or more. That's why we only deal with pretty much 0, 1, or 2. So when we're looking at the rates here, you'll notice I'm using this differential notation here, the dA to the 0 over dt. And the d here represents a change. It's kind of like a delta. And I'm sure if you've done any calculus, you would definitely have seen something like this before. But I don't want you to be too concerned about the math here. These are called derivatives when you've got the d's here, and the d here is equivalent, or at least basically equivalent to delta, or a difference. And if you remember what I was talking about with differences, you know, the rate is equal to the slope, as we went through this, of which is the change in the concentration of A to the N over the change in time. And I went through that in this context up here. Let me show you, if you remember. And I was talking about the concentration of A being on one axis and the time being on the other axis. So that's the y-axis and the x-axis. And we were talking about the initial rates and getting the slopes that way. So we're really just sort of extending that, but we're now using derivative or derivative notation or differentials here in order to express that. So 0 order would be A to the 0, first order would be A to the 1, and second order would be A to the 2. Don't get too concerned with the math here. Just realize there is a link between the rate and the equations that graph that I was showing you earlier. And in calculus, we can deal with a concept known as integration. What integration does is it takes a derivative and turns it into an equation that doesn't require a derivative. And when we integrate this, and again, I'm not going to go into the math behind this, it's not really important to us. What happens is that by integrating each of these equations, we end up with an equation that has the form of a straight line, y equals mx plus b. So if you remember back to your college algebra or your pre-algebra, you'd know that y is equal to m, which is the slope, and then you've got x plus b, which is a constant value. But the whole thing is that's a straight line. So that brings us to this table here, which is a table you do not have to memorize, but is still important to you. And that involves each of these orders here and what the integrated rate law would be for those orders. So for zero order, it's A equals negative KT plus A0, and A0 is the initial amount of A in the reaction mixture, and that's going to be a constant value. So Y equals mx plus B. So I'm actually going to write those down so you can see the connection there between these integrated rate laws and the equation for a straight line. Is anybody unfamiliar with Y equals mx plus B? Never seen it before in their lives? I'm sure you have. I'd be really surprised if you didn't see this before in some of your other math classes. So if we've got zero order, you've got A, which is going to be Y, M, which is going to be negative K. Remember, K is the rate constant. T is X plus B, which is A0, which is the initial amount of A in the reaction, a constant value. Okay, first order would be log of A, and you can see that's going to be Y, is equal to negative KT plus log, natural log of A0. And for second order, it's going to be 1 over A is equal to KT, that's positive KT, plus 1 over A0. All right, so these are the straight line equations we get. I do have a reason for doing this, and I'll get to that in a second. All right, so does anybody have any questions so far? You'll have a little bit of trouble initially, but I promise at the end of this discussion, you'll see that I'll tie it up in a nice little bow and you'll understand exactly what you'll need to do with it. But in the moment, I just want you to see the link between these integrated rate laws and the equation for a straight line. That's all I'm asking you to do right now. Anybody have any questions? Now, the other situation we have here is half-life, and as you can see on the slide here, half-life is defined as the time taken so that half of the original amount of A remains, so half the original amount of reactant. Now, you would have heard the term half-life, I'm sure, in relation to nuclear decay. So if you had uranium-238, which is a radioactive substance, the half-life would be the time it takes to have half of what you started with. And this is really important because when you're talking about something like nuclear waste, for example, you want to know how long it's going to take for the amount of nuclear material you have to become safe. And that would mean that it disappears or turns into something else. And that's what nuclear decay is. You're actually turning one element into another. And for uranium-238, half-life would be the time it takes to have half of what you started with. So if you started with a kilogram, it would be the time it takes to get to half a kilogram. And then it would be that time again to get to a quarter kilogram, and that time again to get to an eighth of a kilogram. So each time, half, 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 and it takes that amount of time to do it. So that's what half-life is. And we actually have these equations here. And in each instance, what we've done to get that half-life equation, I'm not going to do the math here, but what we've done to get half-life, we've set Y to be set Y to be A0 divided by 2, and the time is going to be simply the half-life then. So A0, if you should remember, is the initial amount of material, and half of that would be A0 divided by 2. So that's how these half-life equations are obtained. Again, you don't have to memorize these because I actually give you this table with the problem, which is useful to you because it means you don't have to memorize anything. So it means it's right here for you. Anybody got any questions so far? So before we get too far into this, I wanted to give you a little bit of context for what the zero order, first order, and second order reactions are actually indicating. But here's an example of a zero order reaction where we have only one reactant, N2O4, and the rate equation is actually K N2O4 to the zero. And that means that anything to the power of zero is 1, which means the rate is effectively K. Now, this is kind of mind-blowing, but in this reaction, the rate does not depend at all on N2O4. The rate does not depend at all on the actual reactant of the reaction, which is kind of incredible that this happens this way. But the reason it works this way is because we have this as a catalytic process. So what happens is we've got this platinum, and the platinum here is a surface. Let's make it a little bit flatter. There we go. It's a surface that's got all these little slots on it, kind of like parking spaces for the N2O4. Now, I'm sure that many of you have tried parking at a place like USF. Has anybody ever parked at USF before?
Yes, and if you don't pay, you get a ticket.
Oh, yeah, that's true. But
Yeah.
but would you say, well, I don't know, maybe these days it's not so bad, but I remember whenever I parked there were always more cars than there were parking spaces. Yeah, I don't know. Is that the way it is now?
Well, I went there a few times to turn in my transcripts, and like one time I parked in the parking lot that was like designated for whoever like was staying in the dorm, and I got a ticket. So.
Oh, right, yeah. But anyway, there's always more. Anyway, when I went, this was years ago though. All right, when I used to go out there were always more cars than there were parking spaces. So there was always all these cars were rolling around the parking lot looking for a parking space, and whenever a parking space became available, obviously someone would take it. But the point is there were many more cars than there were parking spaces, and that's the way it is with the N2O4 and the number of slots on the platinum. So what that means is that it's not really the amount of N2O4 that's driving the rate. What's driving the rate really is the number of slots on the platinum. And that really kind of influences more the rate constant than it does N2O4. So the rate is equal to K N2O4 to the zero because the rate doesn't depend on N2O4 at all. And that's always a good rule of thumb to know that if the order is zero, the rate just simply doesn't depend on that. And we'll get to more examples of these later, but that's the upshot of all of that. The half-life, it can be worked out by A0 divided by 2K, and A0 again is the initial amount of A. Does anybody have any questions so far? This is an example of a first order process, and all radioactive decay processes are actually first order processes. So you can see the rate is equal to K U238 to the power of 1. And you can see that the rate does depend on the amount of uranium-238 you have. So the more uranium-238 there is, the greater the rate of radioactive decay there will be. And I think that makes a lot of sense. A lump of uranium that's a kilogram is going to be more radioactive than a lump of uranium that is like half a gram. So that does make a good deal of sense. What's interesting though is the half-life is natural log of 2 divided by K. It doesn't even depend upon how much you start with, which is kind of interesting. And it's just the way the math works out. Anybody have any questions? This is an example of a second order reaction, and this would be N2O2 squared. Sorry, NO2 squared, I should say. So 2 NO2s gives N2O4, and you've got rate equals K NO2 squared. In order for this reaction to go, and I'm kind of alluding back to something that I had earlier. You get rid of this for a second. The situation is that you've got NO2 colliding with another NO2 molecule, which is why it's second order. Because in order to make that reaction go, it requires two molecules. So two NO2s coming together, that would be a second order process. So both molecules of NO2 are involved in what I'm calling the slow step of the reaction, which is probably the only step. And it's producing this product here. So that's how that relates to the rate. And excuse me, the half-life would be 1 over A0 times K. And the half-life here does depend on the initial amount, whereas it didn't in the case of the first order process. You'll notice there's no A0 here at all in the half-life. There is A0 in the half-life for the 0 order and the first order. All right, does anybody have any questions so far? All right, let's look at the kinds of problems that you'll need to be looking at. And this is why I've left this up here along with the equations. So what I'll do is let me get rid of that. So this is the actual data that you'd be presented with. So A or some sort of compound, doesn't matter what. And you'd be given times and you'd be given concentrations of A. Now, if you look at it, you'll see that the time is going up, which makes sense. But look what's happening to the concentration. It starts at 5, then goes to 2.5, goes to 1.67. Excuse me. So it goes all the way down here as the time goes up. And I guess that's what you'd expect. Now, the reason for that is because the reactants are turning into products. That's what's going on. From this data, we'll actually be able to tell whether the reaction is going to be 0 order, first order, or second order. And this is how we're going to do that. The first thing we do is we draw a table, and this table will show the concentration of A, the natural log of A, and 1 over A. So how are we getting those? Let's have a look. Looks like I can't move that. All right. So you got A, which is the data you were given. To get the ln of A, all you do is you put 5 into your calculator and hit ln, or depending on the calculator you have, you might go ln of 5. To get 1 over A, it'd be 1 over 5, 1 over 2.5, 1 over 1.67, etc. Is anybody uncertain about where I'm getting the ln of A or 1 over A numbers? Please look at it. Is anybody concerned about that, please? Now, nobody's saying anything, so I'm assuming that you're all seeing how I'm getting that. Okay, good.
Because in a test, we would be asked to draw this table. I don't know how you got it.
Oh, no, you see the A, you're given the table here up the top. I'm not sure who was talking. I apologize for that. I didn't see the name. Didn't popped up too quick.
That's okay. It's Katie.
Caitlin. Okay, Katie. So do you see you'd be given this time in A? Do you see that?
Yeah. Uh-huh.
You'd have to get the log of A and 1 over A yourself. Do you see how you get those?
Okay, so you're saying you would just type that in your calculator.
That's
and then
right.
You'd come up with those numbers.
Yes.
You have to do it with your calculator.
Yeah, and unless you know logs and in your head, I don't know, but I think you'd probably have to do it in your calculator. Is that okay? All right. So let's look at that. Ignore the slope. Ignore the slope for now, right? Just ignore that. This is what we're doing first. Now, the next question you're going to be asking is, well, why do you choose these specific things? Well, it all comes back to the equation for a straight line. The x value is the time in each case. As you can see, x, time, time, time. Time, time, time. That's for 0, first and second order. The y values, though, are a, log of a, and 1 over a for 0, first, and second order, respectively. 0, first, second. Hopefully you're seeing where I'm going with this. Does anybody have any questions so far? Now, where do we get those values from? The a, the log of a, and the 1 over a. Do you do it from memory? No, you don't have to. Let me show you. Let's go back to that table you're given. All right, there he is. Look, look, look. A, natural log of a, 1 over a, 0, first, second. You're given this, so you don't have to memorize anything. Look at that. A, log of a, 1 over a. All right. You'll see in a second. So what are we doing here then? So we got this table that's got the time a, log of a, 1 over a. Then what we could do is we could draw 3 graphs. A versus time, natural log of a versus time, and 1 over a versus time. Or time versus those. In any case, time's on the x-axis and those other 3 are on the y-axis. And look what happens. When I draw these graphs and plot the points, I get 2 that come out to be a curve and 1 that comes out to be a straight line. Now, if you remember, the integrated rate laws all take the form of a straight line. So whichever one of these pops out to being a straight line, that's the order. So in this case, it was the 1 over a that came out to be the straight line, which is second order. So I know from this that the reaction is second order, because when I drew these points from this graph as a straight line, where time versus a, time versus log of a, time versus 1 over a, this one came out to be the straight line, so I know that that's second order. Does anybody have any questions? You're all hunky-dory with that, are you? I'm finding it hard to believe. Usually somebody has some question about this. All right. Now on the test, you actually don't have to draw graphs. So how can we do that? How do we manage that? All right, let me show you something. Let's pretend, I want to leave this stuff up here because it's kind of important to what we're doing. I want you to look at 2 cases. So let's look at a curve. So that's a curve. If I take points and I've got a curve here, you can see that the slopes of any 2 points here that I've taken are going to be different if it's a curve. So that's a curve. Yet, let me move my chat box here, or my other thing. Here we go, put it down here for now. But if I've got a straight line and I take the slopes between points in a straight line, you'll notice that they're going to be the same. So by using the slope method, we can actually determine, this is a straight, we can actually determine whether a line is curved or straight without drawing a graph. All right, so let's see how we might do that. So that's why I've got or calculate 2 slopes on each graph. 2 equal slopes indicate a straight line. I recommend using the first and second and the last and second to last set of points. Now I might have said something different on the video. It doesn't really matter. It doesn't really matter. You just need to use whatever's, you need to use whatever you're given here. But that's what I recommend. The first and second point and the last and second to last sets of points. So to get a slope, if you'll remember, slope is always delta y over delta x. or if you like, y2 minus y1 over x2 minus x1. I'm sure you remember that. Or rise over run. So remembering that the delta y is going to be whatever's here, which could be a log of a, 1 over a, and on the x-axis it's always time. But these are the y values that are possible here. So when I'm looking at, for example, finding the slope for 0 order, these are the first two y values, these are the first two x values. So I'll go back to that over here. So what I'm talking about is we've got a, and that would be 5.00 minus 2.50, so that's the difference in the y values, and 0.00 minus 80.0, and that would be the difference in the x values. And that's how I'm coming up with that slope. And then you'll notice I take the last 2 points and I do exactly the same thing. And you can see that we come up with two different values. I mean, they look the same, but one has an extra 0 in it. So because the slopes are different, we know that the 0 order one is not a straight line. Is anybody uncertain about how I'm doing any of this? Now's the time to ask. Hello? Any questions? Everybody's all right? Nope, I'm good. That's good. I like to hear that. So we look at the first order and we do exactly the same thing. You'll notice again, we come out with two different slopes. And then for the second order, look what happens. We do the same thing again. We're using, again, the first 2 points, the first two 1 over a values, and then the last two 1 over a values. And that would be the same slope, 0.00250 for both. Now, when I say the same, it might not be exactly the same, but it's going to be close. So whichever two have the closest values, that's going to be a straight line. Sometimes they don't, sometimes they're not exactly the same. In this case they are, but they don't always have to be, but they are going to be close to each other. So that's how I'd know the reaction is second order, and I can do that without drawing a graph. Now the next thing we can do is we can find K. So let's go back to these equations here. And you can see that in each instance, we've got the K values here as part of the straight line equations. The K value is matching the slope. So it's a good thing we found the slopes already, but you can see in each instance, we can actually figure out the K value from the slope. Now you'll notice that in the case of 0, first and second, it's not always a consistent sign that comes out of the front of the K. There could be negative K, that's for 0 and first, and positive K is second. Now the reason for that, and I'm going to show you this here. The reason for that is because of the way that the graphs go. Actually, I'll show you up here. Might be easier. If you look at the slopes on the time versus a, the log over a, you'll notice they're negative slopes, whereas the 1 over a is a positive slope. Does anybody have difficulty determining the difference between a positive and negative slope just by looking at the graph, just by looking at its direction? Okay, that's all I'm doing here. So my point is that m is always going to equal whatever this happens to be here. Yes, yeah, here's the thing. If it's a time versus a, it's always going to be a negative slope. And that means that m equals negative k, but because m is negative, k comes out to be positive. And k will always be a positive value. And we can just get it off the slope. So in the case of this one, it turned out that it was 0.00250, but that's a positive value, but m is equal to k anyway. But if it was first order or zero order, then the slope would be negative, which means k ends up being positive. But the bottom line is k is always a positive value. Does anybody have any questions?
So k is always equal to the slope?
Yes.
Okay.
But sometimes the slope is negative, but if the slope is negative, then the slope would equal negative k anyway, which makes k positive.
Okay, so k is always positive.
K is always positive.
Okay.
Yeah, and that's really all I want you to get from that so far. So I've got it here, zero order, slope is equal to negative k, so k is equal to the negative slope, but the slope is negative, so negative of a negative is positive. Same with first order. In the second order, slope is equal to positive k anyway, so there's no need to change anything. So in this case, it's 0.00250 for the slope, but k is equal to 0.00250, and it's going to have specific units here. In this case, molar to the -1, seconds to the -1. And the slope units are going to vary depending upon what order we're talking about. So it's going to be different for each order. So what I'm going to do now is I'm going to show you how we determine what the unit will be on each of those. So I'll do that down the bottom here. So if you've got zero order, then we have A. The unit of A is going to be molar or molarity, and time, and I'm just going to say seconds just for kicks, but it could be any unit really. And the slope, let's see, it's going to look like this. The slope is going to be molar over seconds if we're just looking at the units. So that's going to be the unit for K. So these are K units we're looking at here. But that's going to be the unit for zero order is going to always be molar per second. For first order, we've got natural log of A and because natural log of anything is dimensionless, doesn't have a unit, then I can't have a unit for the y-axis. And on the x-axis, I'll still have time. And again, the slope would be 1 over s. The 1 is because I can't have a unit from a natural log. So for second order, and this is the one we just did, it's 1 over a. The unit is 1 over m. I want to make that a little bit clearer. And the time unit is still seconds. And the slope is then going to be, again, change in y over change in x, which will be 1 over m over s, which is equivalent to 1 over ms. So it's always those are always going to be the units for each of these different ones, and you can always figure it out. You can always figure it out by doing the units on each of these and then figuring out what the slope unit would be from that, and that will tell you what the unit of k will be.
I have a question.
Yes. Mm-hmm.
So, you know how you said time is seconds? If we have a problem given to us, will it tell us like if it's minutes, seconds?
Yeah, definitely.
Like
Yeah.
Okay.
You'll always be given the time unit. Let me show you where it would be. See if you, in the initial data that you're given.
Mm-hmm. Oh, I see it.
So it'll be time in whatever. So if
Okay.
it's hours, minutes, whatever, days, it'll be up there. So that's how
Okay.
you know what time unit to use. But concentration will always be molar initially molar. Is that okay?
Yeah, thank you.
All right. All right. Any other questions so far? So if you're finding the half-life, then remember you are given up here. Let's go back. You're given the half-life equations up here, which is going to be 1 over A0 times K because we're dealing with a second order process. So that's how I know which equation to use. Now, when you're looking at the actual problem, you see time is 0, and that's the concentration. That's A0. So remember what A0 is. A0 is the initial amount of reactant. So that's the amount of reactant you have when the time is 0. So you'll always be given that. That's your A0 value. So let's look at the math here. It's fairly simple. Half-life. T half is 1 over A0 times K. And K is 0.00250 per molar per second. And A0 is 5.00 molar. So you see that it comes out to be 80.0 seconds. Does anybody have any questions?
Are we going to look at the practice exam for questions like this?
Yes.
Okay, cool.
Yeah. I'm not just going to throw you straight in. Now remember, there's videos for each of those questions as well, right? So even if you don't catch something I'm talking about today, you can always go watch those videos for each of those questions. So it'll be really clear about how you do each one. But I'm not just going to throw you straight in. No, that's not how I'm going to do it. Now, what am I doing here? I was going to, yes, that's right. I was going to show this example here. No, not this example, the one we're looking at. There he is. So I want you to look at something here. Remember what the definition of half-life is. Half-life is the time it takes to get to half what you started with. In this case, you can actually even eyeball exactly what the half-life is going to be because we start at 5. The next point is actually 2.5. And look what it is, 80 seconds. That's what we calculated it as. So it's the time required to get to half what you started with. That's half-life. So you can actually eyeball half-life. In this case, it's easy because it is actually the value there. It won't always be shown in the data, but you should be able to at least eyeball and get an idea of whether or not your half-life value is in the ballpark. In this case, we can actually see it. Does anybody have any questions? Okay. All right, let's go take a look at some resources here and the stuff you'll have access to. All right. So what I'm going to do is I'm going to go to, let's see, so I've got the media lectures here. Reaction orders, here we go. I actually have some more single reactant order problems. And this is them here. And I've got answers for these as well. So you can actually use these for practice before you actually do anything. So it gives you practice at taking the tables that we were talking about earlier and being able to get the order of reaction value of K and the half-life. Because that's what you'd be, that's what you'd be pretty much required to do. But let me show you kind of how you would do this. I mean, what you would do is pretty much what I just told you you would do. You do A, you log over A, 1 over A. You figure out which one has the same slopes for 2 sets of points. That'll give you the order. The value of K you get from the actual slope you find, and then you calculate the half-life of reaction based on the given equations. So it's pretty much what we've just been doing. But what I wanted to show you here is how we could possibly eyeball the half-life here. So here's what I want you to do. So look at number 1 here. You can see that we're starting out at 1.00. Figure out what half would be, and then you could possibly estimate what you think the half-life would actually be. So 1.00, half of that is 0.5. Now 0.5 is just below this. And if you look at the progression, it goes 120, 160. So that would likely be 200. So there it is. Yeah, that's right. So looking at the number 2 here, half of 5 is about 2.5. And that would be somewhere in between 3.17 and 2.34 here. So you'd expect a half-life between 60 and 100. But probably, or no, I'm lying, aren't I? No, 2.34 to 1.1. So 2.5 is somewhere in here. So it'd be between 100 and 200, but probably closer to 100, I imagine, just from that. Let's have a look. See, 91.5 minutes for number 2. No, I'm lying. It was 2.5. Sorry, 2.5 is between these two. Yeah, but closer to 100 than 60. I'm sorry about that. I didn't see which way those values were going. So yeah, so that would be 3.17 down to 2.34. 2.5 is in between, so it's between 60 and 100, and closer to 100 because it's closer to 2.34 than 3.17. Number 3, 0.8 down to 0.17, and you can see 0.4, which would be between 200 and 400, but probably closer to 200. That would be 216. So you can get an idea of how you can sort of eyeball the half-life just based on the data and make sure that you are getting good values for that. So that's practice. It's in that folder. It's also where the extra credit is as well. But I would recommend probably doing that before I do anything else so that you have a good understanding of what you're doing. All right, let's take a look at the kinds of questions you'll see on the test, and we'll go through each of those. Okay. So we're looking here, we're starting at question 2, and you can see that in the actual test, and this is also true of the test you'll be taking, the real test, you're given this table here. That helps you not have to memorize half-life equations, etc. It's all here for you. All right, let's have a look. Consider the data below, which describes the order of the reaction. Okay, so let's see how we might do that. I'm not going to go through the whole thing, but I'll give you the very basics of it. So what you would do is you would take, you've got your table here that's got time in seconds, and then you've got the A, which is in molar, and then you would do natural log of A and 1 over A. You'd extend that table out. So you need a scratch piece of paper in order to do that. And then you'd have your data here for each of these. And then you would find the slopes for time versus A, time versus log of A, and time versus 1 over A. And then you'd see which one gave a straight line. And that would be the one that would tell you which order it is. Does anybody have any questions about that? I mean, it's just what we just went through. Now remember, there are videos for each of these too, for these specific questions. They'll have different numbers, obviously, from what I'm showing you, but yeah, that's how you would do it. All right, let's look at question 6. This is a partial data table, and it's found to be zero order. What's the value of K? Well, how do we find that? Well, remember what the K value is going to be. It's going to be the slope. So for question 6, let me move this over a little bit. There we go. So remember what the K value is. It's the slope. Now, you know this from going back to the initial equations that you're given up here. And you can see in each instance, these are all straight line equations, y equals mx plus b, and the slope is going to be negative k or k, depending upon the order. So all you have to do here, if we're told here that the reaction is zero order, so zero order, and it's going to be change in the concentration of A over change in time, so delta Y over delta X, so it's just going to be 4.78 minus 1.38 over 101 minus 56. Is that right? No, 56 minus 101. There we go. And that's going to give you a negative value. Can somebody do that for me here? I don't have a calculator in front of me. It'd be nice if somebody give me a value for that. Okay. So negative 0.076, which would mean that the K value, remember that K is the negative of the slope, so K is going to be 0.076. So whatever happens, it's going to be, it's going to be close to that. Yeah, thank you. Does anybody have any questions so far about that?
I have a question.
Yep. Mm-hmm.
Just like with test wise, are you looking for like significant figures or anything?
In this case, no. All these answers have a certain tolerance to them.
Okay.
So you have to just have it within that right range.
Okay.
I think significant figures will give you good guidance as to how many things to put down. But in this instance, you're looking for probably at least 2 significant figures, at least 2.
Okay, thank you.
So in the next one, you're told that the reaction is first order and you're given a partial data table. So can anybody tell me how you might proceed with this? Would you just do exactly the same thing as we just did for number 6? This is number 7 we're doing now. So would you just proceed the same way?
You first got to get the natural log.
Oh, you've got to get the natural log, right? So for number 7, it would be first order. How do I know it's first order? Number 7. How do I know it's first order?
They tell you.
It says it in the question.
It says it in the question. That's correct. Right. So it'd be change in log of A over change in time. So what you would do is log 6.20 minus log 2.97 over 49 minus 102. And that'll give you a value. don't worry about calculating that. I think you've got the idea. Does anybody have any questions about number 7? All right, let's look at number 8. All right, anybody have an idea how we might do number 8? Told here at second order in the question. What would you do?
You find 1 over A.
Oh yes, it's like magic, isn't it? It's like magic. It's a beautiful thing. So for number 8, it would be 1 over, changing 1 over A, whoops, over delta T. And that would be 1 over 5.57 minus 1 over 1.79, which is going to be, in this case, what is it? 2 minus 102. Yeah. And that'll give me my slope value from there. Any questions? Okay. So the next thing is the half-life. Okay, so we're told here at 0 order. So what you would do there for number 9 is you would do, it's sort of a 2-step process here for number 9. You would find K, which will be effectively really the negative of the change in A over the change in time. And then you would calculate the half-life, and the half-life is going to be, well, let's look at the equation here. You're actually given it. There it is. A0 over 2K. Down here. Can anybody tell me what A0 would be? And number 9, what would A0 be? 7.84, that's right. Does anybody have any questions? The K value, of course, is what we calculated up here. All right. Number 10, this one's first order.
I have a question about
Yes.
number 9.
Mm-hmm.
So when you mean that you find K, you just mean find the slope?
Yeah, that's right. But
So
it's based on A and delta T, just A.
Okay. Okay, so for that equation for number A, it would be A0, which is in the chart.
Yeah.
On top of 2, and then the slope that you have to find.
That's right. And this is how you find the slope, right?
Yeah.
So you're just putting that value in there.
So, and you multiply the slope by 2?
That's right.
Okay.
Number 10, K is equal to, again, negative of the change in the natural log of A over delta T, and T half is equal to Z. There we go. A natural log of 2 over K, or is it? I think it is log of 2 over K, or negative log of 2 over K. We'll see in a second. Yeah, T half is equal to log of 2, which is 0.693 divided by K.
On a test, will we get that chart?
Yes.
Okay.
It's right here.
Okay.
It'll be the same in the test you take too.
Okay.
I'm sensing a lack of trust here. That, I'm going to give you something different. I told you that the real test you'll be taking is the same as the ungraded copy. Now,
Okay.
that goes for all the stuff that goes with it too. Okay, let's have a look at number 11. What's the half-life? Actually, there was something else I missed there on the other ones, and I do apologize for that, but I'll come back to it in a second. So number 11, we're told that the reaction second order, so what's the half-life? Now half-life, sorry, let's do the K value, which is going to be the change in 1 over A. So a change in 1 over A versus delta T, and T half is equal to 1 over A0 times K. And that's how you would do that. Does anybody have any questions? Okay. The one thing I didn't talk about, and I had meant to do this, was the units on 6, 7, and 8. And as I had said earlier, you can tell what the units are. So you need the value of K, but you also need the units too. So for 0 order, again, I'll just do this, what I was doing here. A is in molar and time is in seconds. So the unit on the slope will be change in Y over change in X. Is going to be molar per second, delta Y. Over delta X. So for first order, again, I went through this before, I'm just doing it again. We've got log of A, and then we've got a unit we don't have because we can't do the log of a molar. We've got time over time is seconds. The slope is going to again be 1 over S. And that would be the unit you put down for that. And then for second order, it's going to be 1 over A. And the unit there would be, whoops, it's not being very kind to me. The unit there would be 1 over M. And then the time is going to be seconds again. And the slope would be 1 over MS. So these are going to be the units in the case of 7, 8, and 9. And it's going to depend upon the order you've been given. So 0, first, and second order. And the units, those are the units that go in each of those units boxes. Okay, does anybody have any questions? Okay, let me submit this and we'll come back to this in a second. So I want you to remember that if you have trouble understanding what's required for a question, for any question on this test, all you have to do is go down here to the practice test 1 videos, which shows you how to do each of those kinds of questions. Remember, there's 22 questions and there's a link for each question here. Does anybody have any questions? All right. Well, that's pretty much all I wanted to go through today. Does anybody have anything else that they want to ask about?
Dr. Musgrave?
Yes, Lonnie.
I had a little trouble with the syllabus quiz. I'm not sure if anybody else had any other kind of trouble with the very last question, like trying to upload a picture into my courses.
Okay,
Maybe
that's
it's
for the
the
lab.
PC that I'm using.
Yeah, that's for the
Okay,
lab.
that's for the lab. Okay.
Let's talk about that. You're in my lab, aren't you, Lonnie?
Yes, sir.
Yeah. Okay. Yeah. Why don't we talk about that in about? Well, actually, no. I guess lab was lab was on Tuesday. All right. Let me briefly go through that. I'll just show you where the thing is. So the directions for doing that are in a video, and the video is it's in the safety folder, I think. Let's have a look. Yeah, uploading scans, pictures of graphs into my courses. So just follow the directions in that video, and you'll be able to put that picture in.
Okay. Thank you.
Okay, no worries. Okay, any other questions? Any other questions? Okay, well, we'll leave it there for today, and I'll see you all next Tuesday.
Thank you.
Thanks for coming.
Can I ask a quick question about
Yeah,
the
sure.
extra
Yeah.
quiz? What do you need to get on them to get the extra credit? Because I know you need to get an 80% to even attempt taking it.
Right. Well, you get whatever you get. So if you got 50%, you'd get 50% of the points.
Okay.
Yeah, so and if you got 100%, well, you get 100% of the points. But you get whatever you get. Here's the answer.
Thank you. See you, Professor.
No worries. I'll talk to you later.
Thank you, Professor.
No worries.